Okay, sample problem 8.13. Use bond enthalpies from table 8.6 to estimate the enthalpy of reaction for the combustion of methane. So the equation is written here, CH4 plus 2O2 becomes or yields CO2 plus 2H2O. That's the balanced equation. These are the bond enthalpy values in table 8.6. These are the energies required to break the bonds for many different chemical bonds, covalent mostly. Okay? So here's what you do. You first draw the Lewis structure for each of the substances in your balanced equation. So 1, draw Lewis structures for everything in your equation, okay? So I'm going to do methane. Now I'm just going to go ahead and draw the Lewis structures out here. It's up to you to practice these so that you're able to do these yourself. But I've done these enough that I know what they are. Okay, there's methane, there's oxygen. I am going to indicate that there's 2 of these, right? Because the balanced equation says there's 2. Now, since this takes up quite a bit of room, I'll write the products below. So carbon dioxide, there's a double bond between the carbon and each oxygen. And then you got 2 waters. May take you longer to draw these, but again, I've done these many times. Okay, so now we've got the Lewis structures and we've got the stoichiometry. Next step, step 2. Look up the bond enthalpy values. These are delta H values, okay? So you look these up in this table. So let's begin. We've got a CH bond here. CH is in the first column and is 414. So I'm going to write 414. And then I'm going to ask how many CH bonds are there? There's 1 there, 2, 3, 4. So I'm going to multiply that by 4. Now I'm going to go over to the next reactant. The next reactant is 2O2. So I'm going to look up O2. And in this table, let's see, O2, here it is. O double bond O, right? So if you got the wrong Lewis structure and you had O single bond O, you'd get the wrong number. So it's O double bond O 498.7. But there's 2 of them. So 2 times 498.7. Okay? Now, let's do the same thing for the products. We've got a carbon-oxygen double bond. Now, I'm going to point out the carbon-oxygen double bond. There's this value here, 745. That looks like that might be it. Yep, C double bond O, 495. Okay. I think that's right. I just want to make sure. C double bond O, 745. I don't see any other COs in there. You just have to be careful with the CO. There's a C triple bond O, that's different. There's a C single bond O, that's different. And that one looks like it's 745, okay? Now there's that double bond, so 745. But there's 2 of them. There's 1 there and there's another one there, so that's times 2. Okay? Now let's do the water. In water, there's an oxygen-hydrogen bond, so we look for OH. 460. Okay? Now, be careful about this. Here's 1 bond right here, but here's another one, so that's 2, but there's 2 waters, right? So if you have 2 bonds within the molecule, but you got 2 molecules, that's a total of 4. So we got to multiply that by 4. Okay? Now we've got all our numbers. So what I'm going to do is I'm going to go ahead and calculate these. For the reactants, we've got 4 times 414 plus 2 times 498.7. Okay, so 2 times 414 4 times 414 plus 2 times 498.7, and you got 2653.4. Okay. The next thing I'm going to do is I'm going to look at the products. I'm going to do the same calculation for the products. Okay. So for the products, we've got two times 745. And then we've got 4. Remember, it's 4 times 460. Okay? So those are our calculations right there. Now, when we do this calculation, actually, I want to point out there's a mistake in here. I just realized it. I noticed I've been going kind of slow on this one. I made a mistake. The table that we have up here is missing something. It's missing a very important piece of information. And that is that if it's in carbon dioxide, it turns out that bond is different. It's 799. I'm sorry. It's not 745. So if you had a molecule like this, H2CO, and it was a double bond O, you would use 745, which is listed here. But this table is missing that if it's in carbon dioxide, use 799. Okay, so I was going a little bit slow in this calculation because of that. And I just looked it up. So 799, sorry. Okay, so now we can calculate the products. So 2 times 799 plus 4 times 460. And you get 3438. Okay. Now we've done reactants and products. Now I'm going to show you the last calculation. What you do is you take the sum, this is the symbol for sum, of the bond enthalpies of the reactants, and you subtract from that the sum of the bond enthalpies of the products. So that would be 2653.4 minus 3438. Okay? Reactants minus products. Now you may recall from thermochemistry that we do products minus reactants, but this particular calculation is reactants minus products because when you form a product, the enthalpy change is negative, not positive. So we're taking into account here by subtracting reactants minus products. So 2653.4 minus 3438, and you get negative 784.6. And that's the heat of reaction. A couple points about this calculation. One is the units. What are the units? Kilojoules per mole in this table. So we're going to use the same units. Another thing to point out, these values are tabulated for gas phase only. Every substance, every bond that's in this table was measured using substances that are in the gas phase. So we cannot use this table for reactions that are aqueous or liquid or solid. We can only use them for gas phase reactions. Furthermore, they are average values, meaning there really is only one molecule that has an HH single bond, so that's 436.4. But there are many molecules that have an NH bond, or HN. On this table, it says that HN bond enthalpy is 393 kilojoules per mole. That number is the average of the strength of the bond or the energy of the bond for different molecules, but not every molecule in existence. So if someone used different molecules to measure these, they would get slightly different values. So when you see these tables, you may see slightly different numbers. Gas phase only, though. Okay? So this gives us a way to estimate the enthalpy of a reaction, delta H of reaction, by using these bond enthalpies. Essentially, we draw the Lewis structures, we count up the number of bonds, we take the sum of the bond enthalpies of the reactants, and subtract from that the sum of the bond enthalpies of the products, and that gives us the enthalpy change for the reaction, and we're done. Okay?